Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, till now we have discussed various analog pulse modulation techniques. We had also discussed about quantization procedure or quantization process. Now we're going to start up our digital pulse modulation schemes. So we'll start up with pulse code modulation systems. So these are the outlines of today's lecture. We'll start up with the introduction. Then we'll define what is pulse code modulation. Then we'll discuss about pulse code modulation generation method or PCM modulator. Then we'll discuss about few basic terms that has been used in PCM, bitrate and bandwidth requirement of a PCM signal. Then we'll describe PCM decoder. Then we'll discuss a quick question in order to understand PCM well. Then we'll discuss about advantages and disadvantages of PCM or pulse code modulation system. Then at last we'll finally conclude with the applications of PCM. We have studied various analog pulse modulation techniques where we saw that the performance was affected by the noise. Noise easily affected our analog pulse modulation systems, especially our PAM. Digital signals imparts noise immunity to our communication system as we can quantify noise as well as our signal well. So we can easily demarcate the noise as well as the signal. So we could selectively reduce out the effect of noise. Hence our digital communication systems are more noise immune. A more specific reason why we would go forward for our digital signals is that nowadays we are using digital signal processors which provide easy and cheap standard techniques to process our signal. So pulse code modulation is a digital scheme for transmitting the analog data. As we had already discussed that most of the available information source are actually generating analog information, and anyhow we must have to convert them into the digital one so that we could avail the benefits of digital communication systems. The signals in PCM are binary, that is there is only two possible states, either high, logic high, or we could say 1, or logic 0, that is low. So they could only have two states. PCM can digitize almost all form of analog data. It is the major advantage of pulse code modulation that it could digitize almost any sort of analog data. So now question is how we are going to generate pulse code modulated signals. So PCM mainly consists of three steps in order to digitize any analog signal. These three stages are sampling, quantization and binary encoding. So initially we're going to sample out our analog signal in order to convert them into the discrete one. Then we're going to quantize our sample signal. We had already discussed in the quantization process that we actually wanted to map infinite signal levels to the finite set of levels so that we could approximate them and finally generates binary codes for our quantized signals. So this particular figure shows the various components of our pulse code modulation encoder or PCM encoder. So initially we'll be having this analog signal, which is our information source or signal generated by our information source. Then we're going to pass that analog signal to the sampling block, which will basically going to convert our analog signal to the discrete one. Then this sampled signal will going to pass to the quantizer, which basically provides finite signaling levels to our sampled signals. Then we'll finally going to pass the quantizer outcome to the encoder, which will going to generate binary bit sequences depending upon in which particular zone a particular sample value will be going to lie. So this digitized outcome, the combinations of zeros and 1 will be considered as the PCM output. So now we're going to consider all three blocks one by one in greater detail. So before we sample, we have to filter the signal to limit the maximum frequency of the signal as it affects the sampling rate. We had already studied in the sampling that in order to reconstruct our signal back from the available samples, the sampling rate should be greater than or equal to the twice of the maximum frequency component contained by our message signal. So first of all, we have to convert our signal band limited so that we could reduce out the aliasing. So filtering should also ensure that we do not distort the signal, that is remove high frequency component that may not affect the signal shape. So as we trying to contain our input signal in a particular frequency band, we should make sure that we should not avoid or eliminate those frequency ranges which actually contain the information signal. If we do so, then definitely we're going to make our signal distorted or information will get loose. So while filtering, we have to make sure that we should not distort our signal. This particular figure shows our continuous time analog signal or time varying signal. So now sampling. Sampling is the process of generating pulses of finite width and of varying amplitude equal to the instantaneous amplitude of the analog signal. So this particular figure shows the sampled outcome. We had already discussed in greater details about various types of sampling methods. In sampling method, we actually going to multiply our analog signal with the pulse train, which will going to generate our finite width and varying amplitude, which is equal to the instantaneous amplitude of the analog signal. So the number of pulses per second is called the sampling rate. So according to the Nyquist criteria, if we want to reconstruct our message signal back from the available samples, the sampling rate fs should be greater than twice of fm, where fs is the sampling frequency, that is number of samples per second, and fm is the maximum frequency of my message signal. So next step is quantization. Sampler output will goes to the quantizer. So the instantaneous amplitude of the analog signal at each sampling is rounded off to the nearest predetermined levels. We had already discussed in the quantization process, it actually maps out the infinite amplitude values of my signal to the finite set of amplitude levels. So this particular process is called the quantization. As in this particular figure, we could see our quantized signal. These are several predetermined levels or stages that our input signal can take. So finally, quantizer outcome or output will going through the encoder. What encoder will going to do is, depending upon our sample value lying in which zone, according to that it will going to assign or generate the codes. So quantization intervals are coded in binary form. So the quantization intervals will be in the power of 2's. For example, either 8, 16, 32 or 64. So these numbers can be represented either by 3, 4, 5 or 6 binary digits respectively, such as for 8 we'll be having 2 to the power 3, that is for encoding 8 levels we could use 3 distinct bits. Similarly, 2 to the power 4 is equal to 16. It means in order to encode 16 different levels we have to use 4 digits, and in the same manner for encoding 32 distinct levels we'll be requiring 5 number of bits, and similarly in order to encode 64 distinct levels we'll be requiring 6 number of binary digits. So the output of a pulse code modulator is a series of binary numbers, each of which is represented by some power of 2. Here this 2 signifies the distinct values of digits or bits, that is in binary coding sequences we are only using 2 distinct digits, that is either 0 or 1. So all the binary coded sequence will again be the combination of these 2 distinct digits only, that is your 0 or 1. So before going to discuss about how we're going to decode our PCM modulated signal, let us quickly discuss about few basic terms that has been used in the pulse code modulation systems. So they are dynamic range and the resolution. So what is dynamic range? Dynamic range is nothing but it is the ratio of largest value to the smallest value of the analog signal, or we could say that it is the ratio of peak value to the minimum value, that is Vmax by Vmin. Whereas the resolution is the smallest analog input voltage change that can be distinguished by the analog to digital converter, or we could say that it is the smallest change or smallest voltage that can be measured by our A to D converter. So the resolution is being represented by delta, and it has been given by VFS by 2 to the power n, where VFS is nothing but your full scale reading, which has been given by Vmax minus Vmin, or we could simply say that it is the difference of peak value to the minimum value. So here the delta is our resolution, n is nothing but the number of bits in the digital code words, and VFS is the full scale voltage range for the analog signal. Then next important points is bit rate and the bandwidth requirement of our PCM signal. So the bit rate of the PCM signal can be calculated from the number of bits per sample multiplied with the sampling rate. So bit rate is nothing but the number of bits passing per unit time or per second. So while discussing the bit rate, we need to tell about how many number of bits per second our PCM encoder is actually generating. So what we have to do is we need to find out how many number of bits are required in order to encode a individual sample, which will get multiplied with the sampling rate, which is nothing but equal to the number of samples per unit time. So the product of sampling rate or sampling pulses with the number of bits required to encode that particular sample will going to give us the bit rate or number of bits transmitted per unit time by our PCM encoder. So bit rate is nothing but is equal to n times of fs, where this n is number of bits required to encode an individual sample and fs is the sampling rate or number of pulses generated by our sampler. So the bandwidth required to transmit this signal depends on the type of line encoding used. Since there are different types of line encoding techniques existent, such as your biphase, NRZ, Manchester, these are different line coding schemes which requires different amounts of bandwidth. So obviously the bandwidth requirement for the transmission of this PCM signal is solely dependent upon our line coding used. So if any line coding schemes require higher bandwidth, then in order to encode through the PCM, our PCM signal will going to demand high bandwidth. And if it is low, it will definitely going to require some lesser amount of bandwidth. So a digitized signal will always need more bandwidth than the original analog signal. Fourier theory already proved that. We had already studied that the bandwidth requirement of an impulse signal is infinite. So in ideal case, our time limited signal will going to require infinite range of frequencies. But the price we pay for the robustness and other features of the digital transmissions. Since in comparison to these demands, digital transmissions or communication systems gives us too much advantages. So that is why we opt for digital communication systems or digital transmission systems. So now how we're going to decode our PCM or pulse code modulated signals. So in order to recover the analog signal back from the digitized signals, we basically follow the following steps. First of all, we need to use a hold circuit that could hold the amplitude values of a pulse till the next pulse arrives. Then we pass this signal through a low pass filter with a cutoff frequency which is equal to the highest frequency component of our message signal, or we could say that our pre-sampled signal or before sampling signal, which is nothing but our information signal. So higher the value of quantization level, it means less distorted a signal is recovered. Here one thing should be noted, that if we're going to increase the quantization level, then definitely to encode those levels we need larger number of bit sequences, which again will going to increase or enhance the bandwidth requirement of our PCM signal. So obviously while increasing the number of quantization levels, distortion will get minimized, but side by side bandwidth requirement will get increased. We basically have to make a trade-off between these 2 points. So this particular figure shows the various components of a PCM decoder. It basically consists of 2 basic blocks, Number one is your make and connect samples, and second one is our low pass filter. What our make and connect samples actually going to do is it will going to take up the digital data, and depending upon those binary bits it will going to generate pulses, and it will going to hold that pulse or amplitude value till the next sample value arise. So it will basically going to process the complete information or bit sequence in the form of blocks. Here block by block we mean that number of bits required to encode a particular sample. So this is the outcome of our make and connect sample. So it will going to generate this type of signal. It will going to make the pulse and hold till the next block arrives. Then again it will going to retain this particular value till the next blocks, and so on. So then finally we'll going to pass this particular signal through our low pass filter, whose cutoff frequency is equal to the maximum frequency component of my message signal. So what our low pass filter will gonna do is it will going to pass or allow only those frequency ranges up to the maximum frequency component of my message signal. So we'll get a smoothen out outcome like this one. So this is how we will actually going to reconstruct our analog signal back from the digital signal. So let us quickly discuss a question about pulse code modulation. So the bandwidth of a TV signal is 4.5 MHz. If the signal is converted to PCM bit stream with 1024 quantization levels, determine the number of bits per second generated by the PCM systems. One thing should be noted that the quantization levels is being given to us is 1024, and we have been asked to find out the bit rate generated by our PCM coder. So initially we need to find out what have been given to us. So maximum frequency component of my message signal, that is the bandwidth of the TV signal, is being given as 4.5 MHz, that is 4.5 into 10 to the power 6 Hz. Then depending upon this maximum frequency, the sampling frequency should be greater than or equal to twice of FM. So we are just considering the limiting case in order to find out the exact sampling frequency. So the minimum sampling rate we're going to consider while calculating the bandwidth requirement, while calculating the bit rate requirement. So that is turns out to be 2 times of 4.5 into 10 to the power 6 samples per second, which is equal to 9 million samples per second. So quantization levels known to us, that is equal to 1024. So the number of bits required to encode a sample can be given as n is equal to log base 2 times of quantization levels. So that has been evaluated as n, that is number of bits required to encode the quantization levels, that is counted out as 10. 2 to the power 10 is equal to 1024. So number of bits per second generated by the PCM encoder can be given as the formula as we have discussed earlier, n times of fs, where n is the number of bits to encode a particular sample and fs is the sampling frequency or sampling rate, which provides us the number of samples passing per unit time or per second. So bit rate is being given as n times of sampling rate, which is where n is equal to 10 and sampling rate is 9 into 10 to the power 6, which counted as 90 Mbps or 90 megabits per second. So this will be the data rate of our pulse code modulated encoder. So now we're going to discuss various advantages of pulse code modulation. So first advantage is its robustness to noise and interference. We had already discussed that our digital signals possess more noise immunity, as well as they have the power to combat the interference. Compatibility of different class of traffic in the common network. As we had already discussed that PCM possesses the capability to convert almost any type of analog signal to the digital one. So it is possible for us in a common network, we could have different types of traffic such as audio, video, images, anything in a common medium. So this is possible due to the PCM only efficient regeneration. With the help of repeaters or regenerators, we could regenerate our information signal back. If we are using PCM in order to generate our information data from our analog signal, then Definitely with the help of different types of encryption decryption mechanism, we could make our information more secure. It is easier to implement complicated communication systems such as our telephone networks. Basically, PCM has been used in voice digitization. So it is also one of the advantage of our pulse code modulation systems. So what are the disadvantages of PCM? In linear quantization, the distortion is more, and to decrease the distortion, the number of levels in the given amplitude range has to be increased. So if we're going to increase the number of levels, the bandwidth requirement becomes high. Since bandwidth is a very scarce resource in communication system, so we basically have to make a trade-off between the bandwidth requirement and the accepted distortion. So these are the various applications of our PCM systems: compact disc, digital telephony, digital audio applications. So basically in CDs, we use pulse coded information to write our disk. Then as we had already mentioned that in order to digitize our human voice signal, we usually use PCM. So PCM has been used in our digital telephony system. There are various other digital audio applications too which make use of PCM or pulse code modulation. So let us take a quick recap whatever we have discussed in our PCM system, or how we're going to generate our pulse code modulation systems. So our PCM systems basically consist of three main blocks, that is your sampling, quantization and the coding. So initially, let us say we'll be having this analog type of signal. Then what we're going to do is we're going to perform sampling. So after sampling, we'll get this pinkish color pulses, and then we're going to quantize them or approximate these infinite amplitude levels to the finite amplitude levels so that we can quantify our sample values more efficiently. Then we're going to provide different types of codes depending upon in which particular zone a particular sample value is lying. Suppose if we're going to consider this particular pulse, it will going to lie in this particular zone, and the code that we're going to use in order to encode that sample value is 010. So for this particular pulse we are using 010, and then for again this particular pulse, as it is lying in this particular zone, the code that we're going to use is 101, that is 101, and so on. So this particular waveform is actually being showing our PCM output. This is nothing but our PCM outcome. These are the various references. Thank you very much for your patient hearing.